Greetings, Professor Van here. This video serves as the introduction to communication systems.
Electronic communication, by definition, is the process of sending and receiving information, data, signals, and messages between two or more locations or points by radio, cable, optical waveguides, or any other wired or wireless medium. According to Republic Act 7925, otherwise known as the Public Telecommunications Act of the Philippines, telecommunications is any transmission, emission, or reception of voice, data, electromagnetic messages, text, written or printed matter, fixed or moving pictures or images, words, music or visible or audible signals or sounds, or any information, intelligence, and control signals of any design or format, and for any purpose, by wire, radio, spectral, visual, optical, light, or other electronic or electromagnetic and technological means. Now, what are the significance of human communication? Communication is the process of exchanging information, either by verbal or nonverbal methods. The main barrier for communications are language and distance. Contemporary society's emphasis is now on the accumulation and packaging and exchange of information. There are numerous methods for communication. First is the face-to-face. This is the most basic. Second is the use of signals. Number 3 are the use of written words. And lastly, this is the focus of our course, electrical innovations. Under electrical innovations, we have telegraph, telephone, radio, television, internet, and computer, and anything that requires electrical signals. Elements of basic communication systems. Let's take a look at the elements of a basic communication system. First, let's start with the transmitter. The transmitter is a collection of electronic components and circuits that converts electrical signal to a signal that is suitable for transmission over a given medium. This is usually composed of several circuits such as oscillators, amplifiers, tune circuits, filters, modulators, frequency mixers, and frequency synthesizers. The transmitter's input is information or intelligence. This can be audio, video, computer data. After processing its input, the transmitter will send its output to a transmission medium or communications channel. This channel provides a means for transporting signal from transmitter to receiver. There are several kinds of medium. For the physical facilities, first, we have the metallic wires. This can be twisted pair cables or coaxial cables. We also have optical media like fiber optic cables and optical wireless system. We also have free space by using the Earth's atmosphere that is used by microwave signals and satellite signals. We can also use the system-specific media like water, which is used in sonar and undersea navigation. Sonar is short for sound detection and ranging. Majority of the noise in the system is inserted in the medium. Noise are random, undesirable electrical energy that enters the communication systems via the electronic medium. This interferes with the information signal. Noise may also come from the transmitter or receiver, but majority comes from the transmission medium. Next is the receiver. The receiver is a collection of electronic components and circuits that accept the transmitted message from the channel and converts it to a form understandable by humans. The receiver's electronic circuits are composed of amplifiers, oscillators, mixers, tune circuits, filters, and demodulator or detector, which is the counterpart of the transmitter's modulator. The demodulator, which separates the signal from the carrier signal, is placed at the receiver. The receiver's output is information or intelligence that is understandable by humans. That's it for the basic communication system. This is a picture of a transceiver. Basically, what a transceiver does is it transmits and receives message in a single device. Examples of these are telephones, fax machines, handheld citizens band radio, cell phones, and computer modems. Attenuation. Signal attenuation or degradation exists in all media of wireless transmission. Attenuation is directly proportional to the square of the distance between the transmitter and the receiver. Types of electronic communication. There are two ways in which we can classify electronic communications. First, if it is one-way or simplex, or two-way, which can be full duplex or half duplex transmissions. Second is if the signals are analog or digital. Types of electronic communication according to transmission mode. The most basic type is simplex. Simplex means that one device transmits and the other device receives. The transmitting device cannot receive, and the receiving device cannot transmit. This is the most basic form. Examples of this are AM and FM radio, broadcasting, cable TV, wireless remote control, paging system, navigation and direction finding, and telemetry. Next, we have half duplex. For half duplex, both devices can transmit and receive, but not at the same time. For example, when transceiver A transmits a message, it cannot receive any message. And transceiver B will receive the message from transceiver A, but it cannot transmit a message on its own. After transceiver A is done sending its message, transceiver B can now transmit a message. While transmitting, it cannot receive a message, and transceiver A will then receive the message from transceiver B, but it cannot transmit at the same time it is receiving. Examples of this are police radio, military radio, citizens band radio, intercom, amateur radio, radar, and sonar. Sonar because it transmits a signal and then it waits for the echo of the signal before it can transmit again. Lastly, we have full duplex. Full duplex basically means that both transceivers can transmit and receive at the same time. Examples of this are telephone, mobile phone, internet, LAN or local area network, WAN or wide area network, and anything that has computer networks. Nowadays, we have what we call full duplex. In full duplex, both devices can transmit and receive simultaneously, but not necessarily between two stations. Meaning, transceiver A can transmit to a second station and receive from a third station at the same time. The next classification is if the signal is analog or digital. Analog signals are continuous signals. For every moment in time, there can exist an infinite number of possible values for voltage or amplitude. The first example is a simple sine wave. The second example, it can be a voice signal. And the third example, it is a video signal for television with vertical and horizontal synchronization pulses. In between the pulses is the signal for one scan line of a television. Next, we have digital signals. Digital signals can only have a finite number of amplitude. In the first example, we have something that looks like a telegraph. So for a mark, we have a higher amplitude, and for a space, we have a lower amplitude. Next, something that looks like an ASK or amplitude shift keying. This is a modulation technique employed in digital modulation. So for a dot, we have a amplitude but only a short burst. For the space, we have zero amplitude, and for a dash, we have the same amplitude for the dot, but it exists for a longer time. Lastly, we have computer signals. I'm pretty sure you've seen this kind of signal. It consists of binary digits, 0 and 1. For 1, we have an amplitude of 5 volts, and for 0, we have an amplitude of 0 volts. Digital signals. Many transmissions of signals that originate in digital form must be converted to analog form to match the transmission medium. This is because we cannot readily transmit digital signals over to free space. Digital data over the telephone network is one example. For the digital data to be transmitted from a cellular phone, for example, it has to be converted into an analog signal first. For analog signals to be processed, they are first digitized with an analog to digital converter so that the data can then be transmitted and processed by computers and other digital circuits. Baseband and broadband transmissions. Baseband information can be sent directly and unmodified over the medium or can be used to modulate a carrier for transmission over the medium. Broadband transmission takes place when a carrier signal is modulated, amplified, and sent to the antenna for transmission. Modulation. Modulation and demodulation. Modulation is the process of changing one or more properties of the analog carrier in proportion with the information signal. Demodulation is the reverse process of modulation and converts the modulated carrier back to the original information. It removes the information from the carrier. Let's take a look at the modulation process. First, we have to input a voice or other intelligence that is usually a low-frequency signal. Voice, for example, has a frequency of only 0.3 kHz to 3 kHz. It will go through the amplification process and the result will be our baseband signal. The baseband signal is one of the modulator's input. The other comes from the oscillator. The oscillator is a circuit that generates our carrier, which is a high-frequency signal. The requirement for our carrier is that it must have a fixed frequency and fixed amplitude, so that we can have a stable carrier signal. The modulator will modulate the carrier signal based on the baseband signal. The output of the modulator is now the modulated signal, which will go through an amplifier to increase its power before being sent to the antenna for wireless transmission. This is the expression for the carrier signal. There are two types of modulation, analog and digital modulation. The time-varying carrier voltage, frequency, and phase, denoted by V, F, and theta, respectively, can be varied. If we are going to vary the amplitude with respect to the baseband signal, which is our intelligence, this is called amplitude modulation for analog and amplitude shift keying for digital modulation. If we are going to instead vary the frequency, this is now called frequency modulation for analog and frequency shift keying for digital. Lastly, if we are going to vary the phase of the carrier waveform, still with respect to the baseband signal, then it is now called phase modulation for analog modulation and phase shift keying for digital modulation. A special kind of modulation for digital modulation is quadrature amplitude modulation, which is the combination of ASK and PSK. To explore the difference between analog and digital modulation, let's take a look at their individual processes more closely. For analog modulation, the input information is a low-frequency analog signal, and the carrier is also an analog signal, but with higher frequency. The output is the modulated signal that is also an analog signal. As you can see here, the waveforms, we have AM and FM. In AM, the frequency is constant, but the amplitude varies. The opposite is true for FM. For FM, the amplitude is constant, but the phase varies. Next, we have the digital modulation. In the case of digital information, the information is a digital signal, but the carrier is still a high-frequency analog signal. The output of the digital modulator is a signal that is analog in nature, but digital in form. The example are shown on the right. The first, this is what we call amplitude shift keying. This is the most basic amplitude shift keying called on-off keying. Basically, when the bit is 1, there is a waveform, but when the bit is 0, there is no waveform. So the amplitude is high when the bit is 1 and the amplitude is low when the bit is 0. It just turns out that the amplitude in this case is also 0 volts when bit is 0. Next example is what we call the frequency shift keying. When the bit is 1, the frequency of the carrier is high, but when the bit is 0, the frequency of the carrier is low. Lastly, we have what we call the phase shift keying. For the phase shift keying, if the bit is 1, there will be no shift in phase, but when the bit is 0, the phase will shift 180 degrees. That's it. Hopefully now you understand the difference between analog and digital modulation. Now, you might ask, why do we need to modulate our signals? Here are the reasons. First, the information signal often occupy the same frequency band. As from our previous example, voice occupies a band of 0.3 kHz to 3 kHz. So if there are multiple voice signals, they will interfere with each other. Therefore, we need to change the frequency during transmission. Next, antenna would be too large in order to radiate a low frequency electromagnetic signal. So it would be impractical if we have to create a very large antenna. Lastly, capacitor and inductor size for tuned circuits would be too large. This is for low frequency signals. So to minimize capacitor and inductor size, we need to increase the frequency. These are computations for the antenna design. From our previous example, voice frequency, it is from 0.3 kHz to 3 kHz. If we calculate its wavelength, which is only equal to the speed of light divided by the frequency, 3 times 10 raised to the 8 divided by 3 times 10 raised to 3, this is 3 kHz. It would have a wavelength of 100 kilometers. So the wavelength of voice at 3 kHz is 100 kilometers. Antennas are designed based on the wavelength. For a dipole antenna, the size of the antenna is the wavelength divided by 2. So for a unmodulated voice signal, the length of the antenna would be 100 kilometers divided by 2 equals 50 kilometers. A very impractical antenna length. So this is it for the introduction.